Yeah, okay. First of all, thank you to be here also this time, and I am happy to be in Flensburg. In the past year, I was here in some periods also 2 times per week during the PhD period of Benedict, because he worked here, I mean, in the project here. But of course, it was my PhD in Loifana. This is also possible. If you find a project here, we can do Dr. Inge, we can do Dr. Ernat. I am involved in both. I'm involved in both because in Loifana, they think that they have a mathematician. They are not a mathematician engineer. I mean, they think, because we work also with these equations. And therefore, I am also involved in this RERNAT, this RERNAT for I think for mathematicians and physics also, they something like that. Yeah, we have both. Okay, let me open this again, this lecture which you can find in our e-learning, and I will recap this linear version of the Kalman filter, and then we will see one possible nonlinear. The name is EKF or the EKF, depends on the pronunciation. Extended, this means EKF, extended Kalman filter. Here, as I told you before, we are trying to apply another kind of Kalman filter with the same hypothesis, let me say, but with a different yeah, idea. But let me go ahead with the repetition or some. I would like to sum up what we did in Kalman filter until now. Now to find the material. Yeah. Okay, let me see. I think should complementary. Okay, this means let me go to another lecture. Or let me see cybernetic. This is the best. Yeah. No, it's just something different. I don't remember. Let me see what happens. Summer semester. Here I do always in summer semester. This means let me see. Okay, let me look here. Yeah. I don't know if it's that is not updated, it's very old. Again, summer semester, let me see. Does not exist. Let me see this one. Could be that is not so old. Cybernetica, exactly. It could be that we can find some discrepancies, but it's just some formal differences. No, linear. What you can find in the e-learning platform is I think is the more updated. But again, these lectures are basically, yeah, the fundamental aspect of Kalman filter. This means if I change some comma, semicolon, because in LaTeX I don't have much time, and sometimes I realize that we have some mistakes. Do you know LaTeX, of course?
Yeah, we work on it.
Also, the examination. Okay, this is more than enough. Yeah, I remember once. I was in the committee for in a conference, and we have to decide. Oh, what I'm doing now? Here, no? Where is this? Okay, we have to decide which paper should be accepted, which not, which one not. And the problem was mm, we have a lot of paper, very good, but the tracks of the conference were limited. This means we have to, let me say, reject some good papers, and we were not able to decide. And I propose, I would like to reject all papers which is not written in the Latin. And the chairman of the conference says, no, this cannot be done. Why that? Because he told us, I don't write in Latin. It's not a good criterion. But anyway, if you don't have a criteria, what we can do? Because LaTeX is, in my opinion, it's a nice software also. I don't want to scientific base, but at least we respect the word. We have to be a little bit more, the mentality more structured to a little bit programming and so on. Okay. Exactly. I will show you later this example. Let me sum up the five equations, which is the basic equations of the Kalman filter. About the model, I think I told you also not only last time. This is basically the continuous, the continuous possible model of the DC drive, which came from probably from other lectures. But anyway, I think I don't need to repeat this. You know better than me. You look, this KM apostrophe is just an annotation in a particular book in which we are considering, if I remember well, radian per second instead of round per second. Anyway, isn't a constant. It's a constant which characterizes the model. We can see that this constant here is exactly the constant here. Basically, the Lorentz length effect in ideal case is exactly the same. It's basically the dual aspect between length, induced voltage, and Lorentz effect. Probably you know better than me, this coefficient. Anyway, this is the continuous system which we want to control. At this moment, we want just to observe, to estimate something which we want. But of course, the idea, as I told you last time, why we need an observer? Because in particular, to control, we are here for cybernetic, and cybernetic means, let me say, control. In the most important, or nowadays, in the most new control strategies, MPC, sliding motor control, we need the states, all states, very often. We have seen MPC, we have seen on sliding, because it's model-based. The control strategy is model-based. This means we have to somehow reflect the model into control. If, for instance, some variables are not possible to be measured or too expensive to be measured, of course, must be estimated or must be observed. Between the word estimation and observation, the difference basically is that an estimation is an optimal observation. The difference, you remember last time I told you a little bit about Lundberg observer. In the form which I presented, the Lundberg observer is an observer. This means we can track something which we cannot measure. But of course, this information which I have is not optimal in the sense, because at least the Lundberg observer which I presented does not consist or does not contain an optimal let me say, procedure. It's not based on an optimal method. Let me come back on the model. Here we have two states, current and velocity, because in the model we can think that we have, at least in this kind of model, without spring. Anyway, it's just a model which rotates. I have an input voltage. And of course, we can think about two kinds of energies. The electromagnetic energy, because of the coil, and the kinetic energy, because I am moving, I have a mass, which is a moving mass. You remember the electromagnetic energy is 1 divided 2 multiply L multiply current square. This means the current is directly connected with the electromagnetic energy. The electromagnetic energy is the integral of the power. If you remember the power in basic knowledge. In the coil, always is the voltage in the coil multiply the current, right? And the voltage is L multiply the derivative of the current with respect to the time. Multiply the current, you have better than me in math, and you have what I told you, 1 divided 2 L current squared plus eventually the energy which I have at the beginning, the integral, calculated from zero anyway. Similar consideration can be done for the other energy which I can see, for the kinetic energy. And the kinetic energy is reflected by the omega. Also, the kinetic energy is quite similar. 1 divided 2 m multiply J in this case. J because we have in the rotation sense we can see here. Multiply omega squared, something like that. Plus, eventually, if I have an initial energy, if the system is moving at the moment which we are trying to observe, we will see that this has a meaning also in the Kalman filter. Or when we implement, I'll show you, because this is unknown. I mean, if I see is the motor is not moving, I can think at least as omega is equal to 0. But about the current, not necessarily 0. First of all, because I can block. Okay, I see that this block, this means I can think that not necessarily 0. The current reflects the magnetic field that could be residual there. You know better than me because I am more mathematician than engineer in this sense, even though therefore my colleague think that I am mathematician. But it's clear. Now, if I block omega, we can consider 0. The current which reflects the flux somehow, which is the residual flux which is inside, but could be not 0. But even though if I don't block, it could be that they have the flux inside, because it could be that this residual residual magnetic energy is not enough to overcome the rest moment. You know, the rest moment, the moment which is I need to move because of the friction, because it could be that we have a magnetic fields residual inside, but it's not enough to move. Probably, because, but it could be. Yeah, about the model, I think I don't need to repeat because it's based on Kirchhoff law. We have one Kirchhoff law, basically the first let me say, line, colloquially, and the second one is basically the Newton law. It's just, should I repeat now? I don't think so, because I already, now look here what I am doing now with the Kalman filter. Assuming that I don't want, or it's too expensive to measure the omega, because for the controller, model predictive control, I need both current and omega in order to predict what will happen, in order to try to control. Model predictive control was okay, the examination. This I need necessarily both. Also in sliding mode control because it's also model based. But let me consider MPC because I like more. This means I have to measure something, because if I don't measure something in output, if I don't measure at least one state variable which reflect one energy, the others cannot be estimated. I didn't have time, I don't have time to tell you about, it could be that later. But I told you about the observability a little bit. If I have time, I'll tell you later. Before starting designing an observer should be, I would like should be reasonable to look if the system is observable. I think I told you a little bit, but it doesn't matter. The observability is the characteristics and the structural characteristic of the system, but also depends what I measure. Sometimes measuring some variables is observable, measurable some state variable. Measuring some different state variables is not observable. If I measure everything, of course, it's observable because I have information directly on everything, but we don't want, because probably to measure the sense, probably in this model, probably is not totally true, because it could be that it's not so expensive to measure omega. But anyway, assuming that I don't want, the current probably is easy to measure. shunt resistance, I don't know what. I'm directly using, I don't know what, I'm not, I'm very bad in measurements. No? But anyway, assuming that I don't want or I cannot measure omega. If I can measure I, the idea is, it is possible to observe and descend to estimate what happens in omega. If yes, yeah, I don't need a sensor. Kalman, not only Kalman, we can demonstrate that using Kalman, what we estimate, even though we measure, we can estimate the current, even though I measure. What I estimate is always better. If the hypothesis of Kalman works, we will come back now in a few minutes, than what I measure. This means to estimate, in general, we say as Lonsville. Yeah, because I save the sensor. If the sensor is not there, cannot be broken down, it's an advantage. In any case, in each electronic intelligent system, let me say, we have always the microcontroller and electronics in which we can implement such kind of algorithms. This means it's not a problem to have a chip inside or a platform in which I can implement this. We don't use a sensor. This means if it's not there, cannot be broken down. We save money. I think in some cases the sensors are very expensive. And what we get is better than what we measure or we can measure. But of course, this is the hypothesis. We will see now the hypothesis of Kalman. The hypotheses of Kalman are guaranteed. But if it's not guaranteed, we can approximate nevertheless. This means, yeah, is in my opinion, but not only my opinion, is useful to understand, in the sense to learn and to apply the Kalman filter. Is applied everywhere. Is applied. Yeah, I don't know if you try to Google Kalman filter. Is applied everywhere. Believe me, I come from industry. My career, I didn't do this gold career at the university habilitation. I come from industry. Yeah. Okay. Let me go ahead. Discretization. As I told you, the idea is to show you an application of Kalman filter, the real application of Kalman filter. We can apply also continuous Kalman filter, but it's a little bit more complicated and more academic in this sense. The idea is to show you how we can apply really the Kalman filter in microcontroller. This means starting from the continuous mode, and now we can see exactly the Kirchhoff law here and the Newton law here. Starting from this, using the forward-Euler discretization, which can be summarized with this assumption, we have many possibilities in terms of discretization. Here is one of them, forward-Euler. Probably this, I told you, another contest, I don't remember, but you heard about this.
Yeah,
It's
a bachelor.
A bachelor. If it exists in a forward Euler, this means it exists in a backward Euler. In fact, exist. I don't have time now to, but probably you heard about Tastin, you heard about Runge-Kutta.
You also did backward Euler in the bachelor.
Yeah, yeah. When we have many discretization methods, this means no one is good. What is the meaning of this sentence? The meaning is, it's not exactly so, but could be considered half valid, the sentence, because we have many dynamics, many ways to represent the system. And of course, we can choose what, in our opinion, also validate, if it's our opinion is could work, is more suitable than the other methods. This means we have many methods to discretize. What is the meaning of discretization? Is in a way to represent a physical system, which we represent at the beginning almost always in continuous form, because what we observe in our reality is continuous, no? Or at least we perceive as continuous. What is just God knows what is. Because in the modern physics, we say that the reality is also discontinuous, quantum, so by not expect about that. No? If you want to represent in a bank system, I would try to start probably directly with a discrete system, because yeah, the state, liability assets, they don't change continuous over time. I don't know when the interest will be updated. It depends on the contract, but not every microsecond, any nanosecond. No, I don't know, probably every day, but it depends. I don't think so. This means we can consider in a sample time 1 day, and then, of course, the model is, I would like to say, directly in discrete form. Here is a little bit different because it seems, in accordance with our perception, that the motor, let me say, moves continuously. No? Okay, if I consider a step, this in particular motor, no, it is this step motor, I think. Probably this can be done, but it's not expected step. I worked in, I told you, my career in ABB, for a research center in Wernigerode, Road, and then in Volkswagen, in cooperation with my university. Now I have a project I had disclosed with Rolls-Royce. Yeah, and we work a lot with permanent magnetic synchromotors. And before I work with asynchromotor, but with this small motor step, typically is small. It's not very, I don't have experience. But it could be that we can consider directly because the movement appears a little bit, let me say, stepwise continuous, right? This means the meaning of this slide here. Now, consider this possible discretization, which we can see the IT, the actual value of the current can be seen, can be represented in this form, I of k minus 1, in which I of k minus 1 means I of k minus 1 multiply Ts. I sample the argument of the I. This could, for I, for omega, for the input, U input, the derivative is basically, we can see here, can be seen, and the future value for the current and for omega minus the actual value. This means I look for to approximate the derivative. Of course, a little bit strange because if this is the actual value, this is the future value, but I don't know the future value. At least here, I don't know the future value. But let me go ahead. I told you the meaning of this. Basically, I do mathematically this assumption. I plug in this information here in the model, and I will obtain two explicit form. Nevertheless, I am using this hypothesis that I know the future. I will obtain a very nice, or the two very nice explicit form. What is the meaning of explicit? Which is the current of tomorrow, the omega of tomorrow, is the function of the current of today, the omega of today, what I can do today. Yeah, I don't want to go in depth about this philosophical aspect backward forward, but anyway, we have this in the typical discretization of the system, which allows to build the discrete form in form, let me say, in form of matrices, in which we can see that Ts, the sample time, plays a particular role in the dynamics, because Ts really makes a difference between this representation and this representation here. Look, if Ts is very small, it seems statically I can represent very well the signal, because T very small means that I try to approximate the signal with stepwise constant function in a really fine way. But what happens dynamically? It happens that this element is 0, this element is 0, or at most 0. This element is almost 0, this element is almost 0. This means this matrix here, which states the dynamics, collapses into the matrix 1, 0, 0, 1, or almost. This means the system is decoupled. And this is the concept which I think I told you very quickly last time, that we fell down in a dynamical system, a represented dynamical system. We are represented now in the microcontroller, which is decoupled. This means measuring the current, for instance, I cannot know what happens in the omega, because we have a 1, 0. We don't have the connections between the states. This is a little bit the the colloquial meaning of the observability. If the system is disconnected, how I can get information of omega if I measure the current? Here we have a system which in the dynamics is basically disconnected if this is zero or small. This means if it's small, is observable, yes, mathematically, but practically I have to really push in the observer to get out the information. Because measuring the current, this element here is weighted by the small value. This means the observer should understand this, and I have to put really a lot of energy. Again, this is the model related to the forward Euler, but it's just a way to represent something which appears to be in this form here. But of course, probably I do some approximation. You remember, I don't consider the noise. And this is the limit of the Lundberger observer with respect to an Kalman filter, which consider also, we will see how in a few minutes, unknown, something which I don't know, or I don't know perfectly, and noise, which is something which also I don't know. Because the noise is characterized also, if the noise is Gaussian, the hypothesis of today is this one. We have also Kalman filters in which we remove this hypothesis of Gaussian noise, but also the Gaussian noise is characterized by a sigma. We say could be here inside. It's not deterministic. This means we don't know perfectly the noise. Or we will see, sometimes it happens, which I don't know, some parameters. Here's a way to represent the discrete system using direct matrices. I would like to skip because I told you last time. Now, the Kalman filter. The Kalman filter basically considers the same element as in the Lundberger observer, but look here. We are considering the system noise, in which basically, if you look very quickly here, the dimension of this vector is the vector as xi, because we consider the same dimension. This means we can associate to a state variable and a vector, which is the noise. We will see that this noise, and today at least, must be Gaussian. But we have also variations in which not necessarily should be Gaussian. What is the meaning? The meaning is what I don't know about the dynamics, because the states or the state vector represents the dynamics. This means it could be that I forgot, I simplified the dynamics instead of 3 states, having considered 2 states. Or I don't know something related to the parameters. But anyway, everything which I don't know, I consider inside these Gaussian variables, which the number of these Gaussian variables is exactly the number of the state which I have. Everything which I don't know about the dynamics, I will try to represent inside the Gaussian variable W of K, because K means again, we are working in discrete form. Also here we can see at the beginning A equal AK, because until now I use AK, and in this book they use A and B. A equal AK and B equal BK. Look, for the output variable, let me come back 1 second again. The output variable in the context of the observer is what I am measuring. Remember, in the context of the controller, is what I want to control. Here is let me say the contrary, the dual method to say. Here I want to measure the current, and we will see how I can estimate omega. This means the output equation in the observer, represents what I want to measure. The representation is always the same, no? The representation based on A, B, C, D in case linear systems. Yeah. It could happen that also, if I want to control the current, the representation for the control is the same, 1, 0. If I want to control omega, the representation of the controller is 0, 1. If I want to control both, identity matters. This is nevertheless is the representation in output of an observer. We will see the Kalman filter, which is a particular observer, Assuming that I want to measure the current, I want to estimate both, because it's always better to use the estimated instead of the measured. It's easy to understand. Look at the word filter. I mean, if I have noise, probably not always, it depends of the filter, must be optimal. If I try to throw away the noise, it's better what I am estimated instead of I am measuring. If I have a measure totally affected by noise, if I filter a little bit, I can assume that is better. But of course, should be not too much, not to be too less, because it should be too much in the sense I would like to say, because otherwise you introduce a phase delay. I don't know if I have a lot of noise, no? And you filter, and then you have a very, very clear signal, but it could be that we have a delay in the signal. Understand what I intend? Because you throw away also the dynamics, which I want to have. This means it should be optimal. A Kalman filter it is. Here again, H was at the beginning C, and in the Kalman very often they use H. I copy for a book. No? In Lundberger or in general, we use C in order to show you the analogy or the duality controller observer. Now, C becomes H typically, not always in the Kalman field. And Y becomes Z. The new thing is just this one, that we have a measurement noise. I told you we have basically two steps, and a prediction and a correction steps. Let me accelerate a little bit. 1 minute to dedicate to show you again this slide here, in which we can see what we consider now as the system, or better to say, the true system in accordance to the frame of Kalman, which we have the deterministic part characterized by A and B, plus a stochastic one. We can see the form is a forward, K minus 1, K minus 1, K minus 1, on the right part K. In which we have also here, as we see in the Lundberger, but we have WK. Look at this a little bit at this hypothesis very quickly. We can see that the normal probability distribution in most cases for W and V must be Gaussian, N means normal, this means Gaussian, mean value 0, and characterized by this covariance matrix. Q is in the process covariance matrix, process noise, better to say covariance matrix, and here is the measurement noise covariance matrix. Very important to repeat this hypothesis. Basically, we assume that these two, let me say, noises are independent. This does not influence each other. White and with normal probability, as I told you directly. Moreover, I would like to say, sometimes normal implies mean value 0, but should be better to write with mean value equals 0. Yeah, again, the definition of, I would like to skip because we have seen last time, of the covariance matrix. This matrix Q. The reason is why we are speaking about matrices, because you have many variables. This means we have to consider the interconnections in between, but here in the middle means colloquially in the middle, in the diagonal, we have the variance. Sigma typically is the standard deviation, which is the root of the variance. Anyway, I would like to speed up. You remember I told you about the equation A, which is the a priori estimation of the state. This means in accordance with the deterministic model, I can predict. Similar to what I told you in MPC. Now I have the deterministic model, I predict. The prediction is based on the deterministic model, but please pay attention here. That is not at an MPC. Look, here we have X hat means always in a prediction, because it's not exactly the true, even though I told you here the true is the Kalman true. Now we will come back what is the true, because the truth doesn't exist. It's a little bit strange what I can say, the reality does not exist I told you, Anna, today that we are fans we are looking on ways to use observer, because the reality does not exist. As I told you, in accordance with some hypotheses, what I am observing, what I am estimating is much better than what I am measuring. But what is better? At least we say that we can get the true, because the measurement is affected by noise. This means in the measurements, in the reality, we have something which is true, something which is not true, or better to say, something which does not belong to the system or to the phenomenon, because it's introduced by errors in the sense. Look, this we will see that this x hat k minus 1 is the estimated state vector in the sense at the previous, let me say, loop of the Kalman vector. This means it's not exactly the same. We will use the previous estimating. Now we will see what x hat is. This is the true in accordance with the Kalman. This means what is the true in accordance with the Kalman? Is what I know. I assume that I know A, in my knowledge. Assume that I know B, plus what I don't know. This means Kalman says, if the reality exists, what I cognitively I know, plus what I don't know. It's easy to understand. This sentence could be acceptable. No? The reality is what I know plus what I don't know. But what I don't know in this context here should be Gaussian and not only independent. And so what I told you also better last time, now I'm trying to do very quickly. I can demonstrate, and I would totally skip the demonstration. I did a little bit better last time, that an a priori estimation of the, we can see here, of the error covariance matrix respect this law here. We can demonstrate, because I can consider two kind of errors. An a priori estimate error, which is the true, Kalman true, what I know plus what I don't know. This is the true. I can speak the true just in the sense, according to the hypothesis, as a Gaussian, normal. I would like to add that, to be clear, mean value 0, everything. And another error is the a posteriori estimate error. And of course, I will generate also this a priori and a posteriori error covariance. I don't know if you remember statistic. Let me go ahead quickly, but you can find also in this slide many information about that. Here, the a priori I told you, the true minus the a priori estimation. The a posteriori is the true minus the a posteriori estimation. It's not clear what this is, not yet. This is clear, what I know plus what I don't know. This is quite clear because at least I show you what it is. Or even though x hat k minus 1 is not clear. Because it's related to this value here at the previous, because it's not clear what is x hat. But assuming that is the estimation of x. Okay, yeah? Doing the calculation is not too difficult but boring. We can find the second equation which estimate, basically we can estimate the a priori error covariance matrix. We can see this is a function of the system somehow, is a function of the previous a posteriori covariance matrix. We can see the recursivity somehow. Plus, this is the limit, because Q is what I don't know a priori. A priori, it seems to be that the variable is characterized by this variance, is easy to understand, but covariance because we have the connections, really colloquially. Let me skip everything because we would like to apply. Look at the equation number 3. If I assume that the estimation of my true, xk is the true in accordance with Kalman, can be considered as a linear combination between the a priori estimation which is particular because it's in a recursive. Plus, look, k, which change over time, multiply this difference here, the name is innovation. What is the innovation? What I am measuring minus what I am observing or calculating, observing is better, in a priori, or better to say, the a priori corresponding variable. I mean, this is something which represents somehow what I am estimating, which is a function of the previous estimation, if you remember, and basically the model which I know. This means this interesting combination. Mathematically, we can see that I can define an optimization problem to calculate kk. Let me show you. Let me skip this boring thing, but you can see. Now, very interesting to conclude that if I now try to consider the trace of the a posteriori error covariance matrix, we can see at the a posteriori error. E, this means the expected that we define our a posteriori covariance matrix. And the trace, you remember, it's the trace, the sum of the diagonal elements, the trace of P. If I do this boring calculation, I try to calculate kk, which minimizes this trace here, I will obtain, believe me, skip everything, skip everything. How I can do? I do the derivative of this expression here. It's extremely boring. If you replace here the expression of Kalman, if you replace here, what is there? This was I already, yeah. Believe me, it's extremely boring, but not so difficult to do this derivative. It is enough because the problem is convex. You have the linear system and the quadratic function, which is the sum of the element, diagonal element. It's a convex optimization problem. You know what intent convex? What? Just 1 minute. Just take this as a definition. You don't have many minima. We have to look numerical. We have an expression of k, which is this one, kk, which change at each sample time, because everything changes, everything is there. Let me explain so colloquially. Very interesting that everything depends on R and everything depends on Q. This is a really important key point. Q is here inside. I don't know if you remember. Q is here inside. Extremely important because this Q and R, we will see together this another parameter which I will introduce now, which is the initial value of pk, is something extremely interesting philosophically because the reality is not possible to be known. I told you last time, I met once Kalman in my life, in a conference. And another professor asked him, I already told you this, ask him when does the Kalman filter not work? Because it seems to be applied everywhere, in Volkswagen and everywhere, believe me, everywhere. If you look, Google application Kalman filter, immense. Not only academically, always. Yeah, I work with Rolls-Royce. If you look at my publication fields with Rolls-Royce, Kalman filter. Volkswagen, Kalman filter. He answered, it's strange that, no, answer so thank you for the question, but it is strange as a colleague of mine does not know, excuse me, today a little bit tired, that the Kalman filter cannot work. Because mathematically, we cannot know exactly Q and R. And also P0, but P0 can be managed. Of course, we have always around the X hat, let me say the mean value we will get in this case is the mean value, and uncertainties, which we have to consider also this. And assuming that I know Q and R, because if I don't know, it's not optimal. I will get the mean value, but also with not the minimal covariance error. because the covariance error is this one, calculated at this point. I mean, do you remember, I would like to minimize pk. K change over time, we minimize pk is this one. Question is, what is pk? Now, anyway, I didn't put the calculation because I have to increase the presentation with 20 slides. Extremely boring, but not difficult, because I have to express pk as a function of kk to do the derivative. Better to do with the computer. Anyway, but the idea. But this is minimal if I know Q and R. Otherwise, could be not the optimal one. Q and R, we cannot know. Okay, this is the 5 equations which we need to implement in the linear system, which depend of Q and R, but also depend of the initial value of P0 or pk. We can see here the initial value of pk, let me say, is the initial error. Remember, I told you at the beginning, if I don't know the value of current, if I don't know the value of omega, I have to put something. And this is reflected in the initial value of P. Look here, in order to start, basically, I need RQ. I need the initial value. We can see here, initialization of the state, and I need the initial value of the error. They are connected somehow to initialize. This is not so dramatic if I don't know this, because the Kalman filter can correct if I know Q and R. Q and R is not known. We cannot know because the reality cannot be known. Also, we will see on the controller, no, we have always to tune something. Always. Of course, with artificial intelligence, we can get at each time information in order to estimate this parameter. But always, we cannot say, now I know everything. No, the reality change. I would like to say philosophically, God creates all the time, and then we cannot know what happens. Believe me. Kalman explained this form. The reality is not possible to be known. We can, with artificial intelligence, particle swarm optimization method, we are working here with some, PSO? Neural networks. Information, we set information, but you have to work steadily, you have to work continuously, because the reality change. We cannot say, now, I did this, everything is over. Again, state prediction, correction, as I told you very quickly at the beginning, we have to stay steps, let me say, inside the sample time. Two equations in the prediction, 3 equations in the corrections. Look here. Now we can see we are represented with this arrows, but we can see here x hat k minus 1, which is basically the previous x hat k. Let me implement in the model. Also, we can repeat everything, and then I will show you in the last part an extended Kalman filter. An extended Kalman. An extended is a nonlinear Kalman filter. A nonlinear Kalman filter is necessary if we have a nonlinear system, or the nonlinear system to be described, to be estimated, or if we need to estimate some parameters, let me say, which generate in the description in the model, and let me say an artificial, in the sense, nonlinear representation. I show you later. Let me now fix again this. Let me open MATLAB. Sie versuchen eine Auto zu klauen, oder?
Ja.
Könnte sein, ne?
Noch sein Gebäude, das Gebäude hat es da, das auf Feuer. Ja. Oh. so ein Fire-Alarm ist.
Ja.
Was findest du nie? Silikon? Ja, Handball, oder? Nein. Also ich auch immer so
We can understand a little bit this repetition. Yeah. Then now let me see the implementation. Probably with the implementation, some aspect can be a little bit clarified. This is a Kalman filter in the linear context. This means the model is linear. But of course, the reality is almost always not linear. But sometimes also in the linear system, we need a nonlinear representation. If we want to estimate, I will tell you later, a parameter which multiply the state, because we have to augment. I show you later. Okay, let me go to here. Too late for you? No, it's not too late.
No.
Let me share. Let me share here. Okay. Did you see Kalman? Okay, here. Okay. Let me open this DC motor. Yeah, you can see that we have the motor, which you know already from MPC and so on. No? This I don't need to comment too much with it. It is the real motor, but very small. Yeah, as I answered you here in one slide, probably you asked me there is an error, but yeah, do you remember I told you in MATLAB is correct?
Yeah, MATLAB was
Because this was different. Huh? In MPC.
Yeah.
But I answer you is probably is a LaTeX problem.
Was it in the LaTeX, right? And I think it was in the model. It was in the model wrong, and the LaTeX was right. It wasn't right.
We can see here I put correctly. No?
Yeah, this is correct.
But in any case, don't trust the professor who does make error. No? It's so because how possible to say also here? No? The reality is in a form of error. Kalman understands very well this because, and the idea is to distinguish or to minimize the error. No? Free from error, that doesn't exist any reality. Also, the true of Kalman is what I know plus what I don't know, which is an error. The error is in a discrepancies no? In between. It's not bad to do error. If we recognize the error, this means it's an experience. If you don't recognize, the error does not exist. The problem in both cases, it's not so dramatic to make mistakes. Or we can consider so. But anyway, better to minimize the error or to learn with the error of the people. Or okay, look, current sensor, 1, 0. CM measurements are means reduction or reduced because I can consider also the position. But if I consider the position and I measure the current, I cannot estimate the position because we don't have any feedback between velocity in this mode, between velocity and position, we have just an integral. We don't have any feedback that allows to say measuring the current, for instance, I can observe, estimate both position and velocity. I don't know if this is clear.
Mhm.
If I have a motor with a spring, then we have a feedback. Or if I have another motor in which let me say, the magnetic fields depends of the position, the rotor, basically also real. Okay, this we have an other complex feedback inside. This means uh, even though I measure just the current, it could be that I can estimate the position of the current of the rotor, because if in the model, if the motor is organized, is structured, that the flux depends on the position, basically it's so, no? Yeah, here I don't see any difference between, I don't know what we have, this representation is the same. Here I use Eger. Probably we tested something, I don't know what. Here we have a possible discretization based on MATLAB. Here I think this means it's continuous to discrete mode. If I don't put any specification, I think this is the exact discretization. I don't know if you remember exponential up to z exponential up to minus ts, something like that. Anyway, it's another kind of discretization. Here I work, we can see, is the last, because sometimes students ask me test the performance with different discretization. I can do, but I don't have time here. But probably you already know. Yes, it's forward. No?
Yeah.
In backward is a little bit different. Everything is forward. Anyway, we can see that we use this forward. Let me run. Basically, what we need here is the, the discrete model, or in this sense, matrices. Let me open, I think this one. Let me see if this works. It's opening. Yeah. Here in this university, Kalman filter is not offered and in some courses.
Maybe in certain control systems free, but it was not offered when it was in the bachelor program. So
In the bachelor program.
yes, so in the bachelor program we have control systems free, and I'm not sure if it is there on the topic, but it was not offered for us.
I think we don't need to speak about this model here, because this is, we have seen it in MPC. Let me share because I forgot. I think, let me share for Osama. Yeah, here we have basically the matrix A, B, C. This is as in Kalman filter. Excuse me, as in MPC. Here the difference CMR is 1, 0. This means here is this is the vector we can see from here, current and velocity, and I will take here the current from both. Let me analyze what we have here inside. Look, we have an input. We measure the current selected by this structural measurement. We can see that I can add noise. And the idea is to estimate the current, even though I measure, because I already told you there is a theorem, Gauss-Markov theorem, that Markov that says that what I am estimating, as I told you before, is better what I am measuring in accordance with the hypothesis. And velocity. Here I put also, I don't have time to tell you about why I'm putting kx, even though I don't use for the recursivity, but sometimes it's used to analyze the performances, how good the estimations on. Anyway, if you want to work with us in Kalman filter, we can really go in depth extremely on this aspect here, because we have an extremely complex Kalman filter here. Together with Fritz, together with Anna in this sense in this project, UKF or ensemble Kalman filter, we have a lot of variations in accordance with the application which we want to consider, which we have. Here is just for if I have more time. Anyway, let me go ahead here. Here is just the presentation here inside. It's a shame, but not so shame. I'm not using this embedded function. I'm using the interpreted. I think it's also in MPC I use the interpreted. The idea is that, in my opinion, didactically, practically we use also always embedded because we can flesh out the electromechanical control. Here we have to change what is the meaning flesh out. This means just once we, let me come back, I clarify this because in Kubernetes is important, this concept here, but probably you know already. When we are satisfied with this performance, in which we can, let me say, let me say, optically what happens in the comparison, or we can measure the integral of the error square, or we can look at the diagonal elements of the a posteriori covariance matrix. I forgot to say, but last time I told you, I think, that here we can see that I minimize the sum of the diagonal elements. But there is a theorem that if the hypothesis guarantees minimizing the sum, also the singular element is minimized. This means the error of the current, error of the velocity. But it is a little bit more advanced, and there isn't a demonstration. Because they are orthogonal. I give you a word. This means to minimize the sum, I minimize also singularly the error. Think about it, and then in German is Dreieck again, a triangular with 90 degrees. If the hypotenuse is the minimum, is also the minimum of the cathete. This is a little bit the same. In the hypothesis, we guarantee the orthogonality. Let me give you some keywords. If you go ahead with me in PhD program and the Kalman filter, we go in depth also in these theoretical aspects. Yes, it's better a little bit too intuitively, because also this orthogonality, if we have to demonstrate, is not so self-evident, we say in German. But we can intuitive, if some hypothesis guarantees, we can assume that it works. I mean, not only the sum, but also singularly. The concept is connected with the orthogonality. Therefore, this analogy with the in German Dreieckige. A triangle means 90 degrees? No. Rectangular triangle in German.
Yeah.
Yeah. A triangular with 90 degrees.
Yeah.
Here, as I told you, flesh out means when we are satisfied, we throw away everything, this in particular, but everything, and we flesh out just the algorithm. And then, of course, we have some technical aspect to be fixed, but this is always not a problem, because we have to flesh out the algorithm, which I will show you now. It's a shame not directly clicking. Here we have an M file, which is our Kalman filter, but I would like to show this. Therefore, didactically is important, this scheme here, because we can see that we can see here basically all the states. To remember, x hat k minus 1. We come back. Better to say, here we have x hat k minus 1. Here we have x hat k, because it's in the delay time. It's the previous one, which I need for the next step. And as I told you, we need also the a posteriori covariance matrix. Here we have a pk minus 1, pk minus 1. And here we have a pk. If you want, I can show you again the lecture. Let me share. we need the initial value for both, which I can put in this case in this Z block. If you use an embedded structure, you have to write inside. It's probably you know how we can do. But in the algorithm, we can see here that we need a pk-1. At the beginning, I put it, that doesn't matter what. I mean, if I know, better. If I know a little bit where the error is. Very important in the nonlinear variation, variation of the Kalman filter, because in the linear, theoretically, we can demonstrate, it doesn't matter what you put, we'll find the unique minimum of the a posteriori covariance matrix. In the nonlinear, it could be, if it's not close enough, we have an optimization problem which is not convex. This means cannot converge totally, or can converge not at the minimum. This means we have a variation which is larger than we want, or not what we want, because we don't know what we want. Okay, we know that that should be the minimum, but we don't know what is the minimum. But sometimes really we have the feeling that it's very large. This cannot be the optimal. And when I say I don't know what we want, well, I intend we don't know what is the minimum. No, God knows in a non-convex problem where is the minimum, kk, and how much is pk. I don't know if this language can understand. If you have many, in English, is valets, no? In an optimization problem. That means I have to find the minimum of the minima, the global minimum. Not got to know where is. We use this genetic algorithm, you know this? A little bit, the PSO, which is quite similar to a genetic algorithm to look where is, no? With the birds, they fly to look at this domain. We can apply also here. Of course, by master thesis. What I'm telling you about? I don't remember. Now I lost myself. I told you. No, it is important. It is important the initial condition in nonlinear case, because if the model is nonlinear, we end up is not convex optimization problem. This means if we are out of this best, let me say, convex region in which you have the corresponding global minimum, it could be that in the best case that we fell down is in the minimum, which is not the best one. This means larger, but we cannot estimate if really this is the minimum, because we don't know what we want or what we expect, it better to say. We want the minimum, the global minimum, but we don't know where it is. We don't know how it looks like in terms of estimation. But sometimes we can guess, because it cannot be. I mean, you have a feeling about it. Therefore, sometimes it's important to have a feeling where could be the minimum. I mean, if I'm working as a motor, the motor is small, I never think to put in the current and the residual current at the beginning 1000 ampere. That's makes no sense. Because the motor will be destroyed. This means we can say that more or less I suppose that the minimum, also the velocity, we cannot put, I don't know, a million rounds per second. This makes no sense. In this sense, try to understand that we have to know a little bit a priori knowledge. And sometimes we put some reasonable values in this sense. Because the trace if of the matrix pk, if the problem is not convex, at many value. Okay, now I think I remember what. Here the initial value can be put here inside. If you click here, you have the possibility to put 4 values. Here you have the possibility to put 2 values. And you have the measured current. Please pay attention here, UK is delayed because we have UK -1 in the forward oil. Yeah. Here we have this max, which we don't have in the embedded, realizing a vectorialization of this. This means here inside, we will see that we have to reorganize the value. This is not so comfortable, but didactically, I prefer to show you this because we can see this recursivity a little bit. Otherwise, if everything is inside, probably easy to be realized in sense of programming. But sometimes it's not totally clear. This x hat k minus one, which today I told you very quickly, but I hope that I was able to give at least a feeling. Let me now show you the software here. Let me share now. This here, Kalman motor, the function. If you go inside this interpreted, you can see that you can find the name of this file, but it's exactly Kalman motor. No? The name, if you want, I show you. Even though, yeah, we're already here. No? If you look here inside, this embedded is organized. You have to look, you have to declare the number of outputs and the function which you call. In embedded, you don't need, because you click it, you appear directly the M file, which is this one. Let me show you the M file. Let me share. I don't know, I shared? Yeah, I think so. Okay, yeah, it's there. Sometimes I use the same name, no? But does not matter. This is the name. It's not the name of the function. It's the name of the function, but not the file. It's the name of the. I'm more happy to work with embedded. Global, because in this interpreted, we need to transfer from this value here. Otherwise, you don't need, if you used, because you can put also here as in the embedded, if I remember well, you can put also here as an argument of the function. But probably you know better than me, and the embedded. Because I used always, I copy already prepared file. I don't have time to, but I think we can put also here. Anyway, it's clear. No? X, what I need each time, should not fix once full. Once I have to calculate each time, come from the previous. And here is, at this moment, assuming that I don't have any changes in the parameter, now we will see exactly now what happens. And then look, UA, I mean, X1 was the input, delayed input. I call UA. The second variable, what way I measured. If you want, I come back in the max. Do you want to see the max? Why this is yn, which is the current.
The second.
Yeah, it's the second in the max. And then the fourth one is this previous state, come back from the output. Basically, x hat k minus 1, because it's delayed. Excuse me, today I'm going fast, but they come back then. Now here, we can see that in this case, in the embedded, it is in this sense, I have to reorganize the four values which we have in the max. The max is something which vectorial, basically organize in the column vector, if you want. And then I have to consider the element 5 and 6, and that you have to consider the row instead of the column, and then I have to put also the element 7 and 8, so which is in the column in the second row of the covariance matrix. Up, and this sense is the a posteriori covariance matrix, no? Pk minus 1, because it's delayed. Here is already delayed. X is delayed. X hat k minus 1. Yeah, I changed the name. If you don't want changes, it does not matter. I don't know why I changed. We measure the current, first variable. Here I change again the name. This is a possible variance of the measurement. This means I transfer of the measurement. Look here. You remember the concept of last time? Small r means small uncertainties in the measurements, because r represents the variance, covariance. In this case, it's the variance, because we have just one measurement. It's easy to interpret. No, and the variance means very small or relative small. No, very small doesn't mean anything. But anyway, we will see respect to omega, to q. It's very small if I remember well, when we look. This means I trust a lot the measurements. Means that I will weight the innovation more. KK will be emphasized, larger. Because you remember, R is present in the denominator of KK. I show you in order to understand this concept. Let me conclude here. QX, where is QX? Here. It's not so much smaller. It seems to be that I trust more, I trust more the measurements. But let me show you this aspect here is extremely important, which is written in the slide. Look, larger value of Q means small value of KK conceptually. Larger with respect to Q. With respect to Q. Means very small KK, because this is in the denominator. R works in the denominator. But very small value of KK means that I don't trust the measurement. Why that? Because everything which came from the measurement is minimized. Please remain quiet, no? Because I don't trust you. If R, let me say, infinite, KK is 0. Means R infinite and the Gaussian with very large variance, covariance, variance, that's in this sense. In this sense, it's variance because we have just one parameter. Very large deviation. This means we cannot trust the sensor, make a lot of mistakes. This means go ahead with the estimation, with the a posteriori estimation, just with a priori knowledge. What I know. Because what comes from the measurement is not trustable. A priori, because I bought a sensor which is not so cheap, but it's not so precise. Q works in P minus. We can see if it's Q, for instance, we can see from here. If Q is very small, we have the same situation. Because V is very small, theoretically 0. We can see that for different reason, we trust the model. Because Q very small means the a priori knowledge, our cognitive aspect, is extremely strong. We have a really precise deterministic model. It's for other reason, but I never trust the model. In the first case, if R is large, I don't trust the sensor, and I have to trust the model. It doesn't matter how the model is. I don't have other choice. Indirectly, let me say, but in effect, I trust the model. Because this should be very small or the 0. For Q small, this means again, now, again, the information about the model is quite precise because the variation, the noise, the process noise is very small, or at least is characterized by the very small variance, covariance, and so on. In this sense, I trust directly. Think about this a little bit at home. You can work with this Q and R. Typically, we have method, neural network based particle swarm optimization method, which try to estimate Q and R at each step time or from time to time. It depends on the capability which we have, the calculation capability which we have, in order to set the best one. Because everything changes, we can see also over time. Just to give you some information. Let me run a little bit. Before running, let me conclude with the file. Yeah. Look. Okay. Here we have the matrix, the equation B, a priori, excuse me, estimation of the covariance matrix, error covariance matrix to be precise, but it doesn't matter. Sometimes it's so. Equation B. Then we have the equation A, the a priori estimation of the states, in which here is x hat k minus 1, because came from the previous, which is delayed. And also B is the map of the input, multiply UK minus 1 is delayed. But this is not came from, this is directly from the measurement, the input. Here's Kn, the Kk we called in the lecture, equation C. And no, excuse me, this is the equation D, excuse me, this is the equation D. This is the equation D, which came from this hypothesis, which is the equation C, after the optimization method or procedure, no? The derivative of the trace of pk with respect to kk. And the solution is this. Excuse me, the solution is this. Of the derivative of the trace of pk with respect to kk. This is the solution. And what is pk? This. The calculation is boring, but it's not difficult. Is the output. And the output, this is just to monitor, for debug, to look at the performances. I don't have time to tell you about that. And then we have the new, let me say, estimation of the a posteriori covariance matrix, and here the new states. And then loop again, loop again. Let me show you what happens. I hope that works. No? The Kalman say that doesn't work, no? But in another sense, in another sense. It could happen that sometimes at the end of the lecture, the student asked me for some variations, and then I forgot. Yeah, sometimes some particular variation, then it doesn't work or doesn't work well, and then I forgot to come back to the. Yeah, it's running very slow. Because probably we changed the teeth several times, something like that. Let me see what happens here. It could be that it is enough to. I know why, because I am reading from that. It could be. Yeah, this is enough. We don't need to. Look, let me share. You can see it? Let me share. Yeah, should be tuned a little bit better. But the velocity which you have to track is the yellow one. And from Kalman, I think, let me see, it should be this. I confirm now. Yeah, because the color is on. This is yellow, and this is blue, right? Yeah, I remember well. Yeah, again, from home, I have to track yellow, and the Kalman is the blue. Could be also better tuned. We can try together once. But nevertheless, we can see, even though I have some errors in the initial condition, I have some noise, not so much. The Kalman, it seems to be that in 0, I don't know, 0,05, something like that, or probably 0,08, something like that. It seems to be that gets the solution. And that we will get the solution independently of the initial condition, because the problem is convex, at least mathematically. But also the simulation, in the sense I would like to say, that respects, because it's in a machine, and don't forget it's in a machine. It could be, not could be, really, the covariance, the trace, is not totally convex. Numerically, this means we have many valleys. It depends on TS. But we will get nevertheless very close. I don't know if I understand. Convexity is mathematical abstraction, even flat. But if you have to consider what the computer represents something stepwise constant, this means it could be that the program will stop somewhere, not exactly at the minimum, close to him. I mean, numerically, we have always a difference between the true and the true, the continuous and the. Let me tune once, and then we will start with the nonlinear. what we want to do. What do you think? If I increase this, typically is done by a neural network. No? Look something. The algorithm is quite complex, but we have also application, also publication in this sense. They say, "Man, please pay attention. I would like to, for optimization problem inside the Kalman, I would like to trust more the measurements. In Europe, what happens? I give more energy to the innovation. This means it could be, I can imagine that react stronger. This means try to follow the yellow a little bit more prompt, but I will include more noise because we have seen that the measurement with noise, look, I am trusting more the measurement. Did you agree? No, no less. Excuse me.
No.
I'm tired.
Because it's a denominator.
Less, what do I say? I increase now R. This means I trust less. If I increase the denominator, KK decreases.
Yeah.
This means I trust less. This means I think that will be slower. Let me do what we originally want to do. Let me trust more the measurement, right? In this case, let me reduce this. If I reduce this, indirectly, I trust more the measurement. I have just two possibilities. Trust the measurement or trust the, of course, the optimal is always a little bit, therefore neural networks on. No? But let me to check what we are waiting. Now I increasing Q. This means the model is not so trustable as before. This means I trust more. Yeah, I trust more the measurement indirectly. Check if I told correctly. No? Let me see what happens. In my opinion, should react quickly, but also with more noise. Let me see if my thinking is correct. Sometimes, did you agree?
Yeah.
Because
you have to run them, save them.
but I think if I run a save automatically, no?
Maybe no.
I don't know. I don't remember this option.
Previously.
Not much difference. Yeah, a little bit probably. Yeah. Or because before we reached the 0.8, now this is earlier, a little bit, no? Or not? Oh. More or less the same, a little bit earlier, right? Let me increase a lot. But you can see a little bit more noise, not much. Let me do again. I remain here, but believe me, I am doing. Let me try to do something like that. I shared the form. No? I didn't share, but does not matter. Let me show. Where is? This is. It could be that we are in a saturation situation. Let me tune again. Yeah, we don't have what we want to have. It could be that we are You see now? But I think we are already in saturation. Let me try again with a beta P0 should give us okay. It's very lazy. Look, this is really something which must be clarified. If I put 0, I don't know if you see now at all. If I put 0 in P0, this means, where is here? You say into the Kalman filter that you are, it is already at the goal because the initial error is 0. This means you don't have to do anything. Because you already, if you put 0, you're already at the goal. Because this is, let me say, colloquially, the initial error. If the error is 0, Kalman filter is quiet. It's sleeping. It's sleeping because that's the minimum possible error. And before is understand, we are basically in a steady state situation in which we cannot improve its performance in this sense. Let me show you what happens now. What is? Yeah. Well, don't happen anything. But should react. Why it does not react? Now I have to proceed with the nonlinear. Let me try it again. Why does not react? Should react. Otherwise, there is an error somewhere. Check at home why it does not react. Could be that there is something which I... No. It could be that really... Ideas?
Is there a problem with the resistance of the motor and the so because you're using 2 times the same variable.
No react.
Variable. Oh,
Too much. Yeah, 1 second. This P is too much. But it seems to be the reaction there. This means, yeah. Let me quickly try now. Yeah, now it's very quickly, but extremely noisy. Because we trust a lot the measurements. Yeah, okay, this is real. Therefore, we need some intelligence to calculate. Oh, yeah, we can see now what I would like to see. Extremely quickly get the results, but very noisy. The reason is I increase Q much more what I thought in order to trust more the measurements. So we have information from outside that the system react, but of course we pay this in the price in the variance. But you can see that I think we get, yeah, you can see that he get the results somehow, but of course with a large variation. No? Yeah, it's a little bit visible, the yellow. No? Okay, non-linear. 10 minutes, yeah, okay. No, it doesn't matter. The nonlinear case is not, at least in UKF a little bit more, I don't want to say complicated, but more articulated than in the concept. But the nonlinear Kalman filter is a linearization of the approximation, let me say, of the model, if you want, around of the x hat, around the estimated value. Let me show you a little bit the equation very quickly. We have again 5 equations. Here, no? I will upload later. Let me go ahead with also the software. Let me share. Let me share here, no? Look here, basically, we have the prediction, which is done with the nonlinear model. No changes. We realize and the discretization. Here is very important, for instance, an explicit discretization, which I can have in a prediction. In the backward Euler here, we have something xk, which depends on xk. Now, this means it's not so easy to work with the backward. We can simplify, we can use some tricks. But anyway, to predict, we need an explicit model. This means the present must be a function of the past. Or if you think of the future must be a function of the present. Yeah, the output could be also nonlinear. Now we will consider just the states nonlinear, but the nonlinearity could be in the dynamics, but could be also in the output equation, which at this moment we have seen just in a sensor, but could be included also in the model in the output equation. This equation here is formally the same, but the matrix A, is written somewhere, I think, is probably later, yeah, is the Jacobian matrix of my field. The field is this. Basically, it's, roughly speaking, I don't have time to tell you much. But it's interesting, nevertheless, if you look at the lecture, there is really an interesting, more clear interpretation of the Taylor approximation. But you can believe me, the derivative is always related to the Taylor. Of course, here we have 2 variables. This means we are speaking about the matrix. This is Jacobian, probably Matthew, remember, no? Jacobian matrix. Yeah, calculated, we can see here, at the previous estimated state. Therefore, I told you in linearization, when I say it's linearization of the nonlinear system, is not totally correct, because linearization of inside the Kalman, because the nonlinear system remains. We have to see a little bit more theoretically, but keep in mind, as an input is a linearization around one possible approximation. In the UKF ascended, we have the linearization not only here, on the sigma point, basically at the point on the variation, the variance. In this sense is more the sense detailed, but of course, then we have to sum up somehow this information. But for the calculation load is much heavy. But forget at this moment, but both are related to the same hypothesis, but we linearize considering not only, let me say, the possible mean value, but also the sigma point. So just to give you also the nomenclature of sigma points. But of course, we don't know where the sigma are. This means we put some points. Anyway, the rest is the same. The unique things, if the nonlinearity is in the output, instead of here the a priori estimation, we put the output function and a function of the a priori estimation. Do you remember here it was h capitalized multiply xk hat minus 1. What is h capitalized here is the Jacobian of the output. This is the unique difference. Let me see if it's written here. Yeah, it's written here. Everywhere h capitalized before was also the Jacobian. Because the Jacobian h was 1, 0. But it's the Jacobian of what? Of I. If the output set of k equal I, the current, the Jacobian of I is 1, 0. Look a little bit at home. H capitalized as before is the Jacobian. And here we have a directly nonlinearity. But it's as before, because before we had H multiply X, what we measure, xk hat minus. We measure H with the Jacobian multiply X H at minus. Here we put directly the nonlinearity. This is a little bit the sense, but it's similar as before. No? Before we didn't change anything in output. Also here we didn't change anything here. Because H multiply X K at minus is exactly what we measure. And here exactly what we have in output. Because here could be also more than we measure. A little bit difficult to understand because I don't have time to show you an example. But think about that the nonlinearity could be also in the output. And a part of the model could be also in the output, which includes what we measure, but not all. Here a little bit the more in depth about the Taylor approximation, but let me go to the simulation. And in particular, I would like to show you an artificial, not artificial in the sense, a nonlinear representation of a system in which the system is linear, but because of the estimation of a parameter, we end up in a nonlinear representation in the microcontroller. This is more interesting than, let me share, a nonlinear system, and physical nonlinear system, because here we have nevertheless a nonlinear system, which in many applications is very useful because, look at this, because look at this problem. The problem which I presented before. But assuming that we have a resistance to be estimated. I mean, assuming that I don't know the resistance, you can consider also L, you can consider also J. How many parameters I can consider? Here depends of the observability. I don't have time to tell you. I can enlarge, we can see here, with respect to before, we have 3 states. Because I consider what I want to estimate as a possible state. I end up in a nonlinear system. Why that? Because we have the product between R, that is in this representation, is in a state, which multiply another state. And multiplication is a multivariable function, is nonlinear function. We can demonstrate. I can also augment, we say, an augmented state, considering L also. I can do that. They say this system remains again observable. We can demonstrate. But of course, increasing another parameter, I cannot find this observability, and the Kalman filter don't find the solution. Because if the system is not observable, this means I don't have, let me see, enough measurements, or look at what happens here. 0, 0, 0, 0, 0. I have in the matrix information not deterministic based. Why that? Because the derivative of R equals 0 means that deterministically isn't a constant, as we want. R isn't a constant. But inside the Kalman filter, is a constant, is a Gaussian constant, characterized just by its, in this case, in the state, Gaussian density of probabilities by mean value 0 and its variance in this sense, which determine also the covariance matrix 3 times 3. The rest does not change in the sense, look, this is basically what I told you, what I know. We can see this Rk is a constant because Rk is equal to Rk minus 1. This is the model. No? Once I do the discretization, we can see this nonlinearity. No? Rk minus 1, which is an augmented state, which multiply the current. I mean, in the representation, if I wish to measure, to estimate the parameter, I end up in a nonlinear system, even though the system is, let me say, linear time variant, because R I can consider the change over time because it changes the temperature, but I can consider the variable which changes over time. But in the representation, at least in this representation, it's a nonlinear system. This means you can see that yeah, I am using what I told you until now. I repeat it also for you here. I'm using now the Jacobian, and believe me, is this one. You can see a 0, 0, 1 because here's the, if I consider ROK equal ROK minus 1, the first two component is 0, and then we have the derivative of what? Of ROK with respect to ROK minus 1 is 1, because if you look the derivative of ROK, which is equal to ROK minus 1 with respect to ROK minus 1 is 1. Try to do at home, I think no mistakes. Now I show you directly the simulation. This is all. The rest is, again, the same as in the linear system because the nonlinearity is in the state. Could be also in the output. This is a little bit, we have to consider also the Jacobian of H not capitalized, which I indicated with H capitalized, which here does not change because I measured as the current. Let me simulate, and then we conclude this lecture of today. Let me see. Fix, 5 minutes.
Das ist alles gut. Ich hatte nur Angst, dass ihr hier fertig seid und du jetzt wartest und ihr dürft euch da auch von dem Kuchen nehmen.
At the end. The guy, did it solve the solution? The guys.
Noch nicht.
Did you find
wir
it?
sind
Ganz nah. I try to do publicity to our problems so we can get good students. No?
Sehr gut.
5 minutes, get there.
Good.
If you come to us each time, there is something like that. I don't know if this could be more attractive. Could be. Maybe here there is a real interesting project. Believe me.
Yeah.
You tend to talk Fritz an. Ja, very interesting proof stand auf Deutsch. Experimenter setup. Really interesting. Yeah, this university. Okay, let me now show you the simulation. If the nonlinearity is the structural nonlinearity, physical nonlinearity, x squared is easier. It's easier because we don't have to add something which is structurally unknown. This R is a Gaussian variable, which is characterized by the covariance matrix, the variance, basically. I show you now what is in the simulation. We are ready. As I told you, this is not included in the examination, but my idea was to tell you because I have to do publicity for our course, for our project. Here we apply always the Kalman filter because very often in such kind of systems, we cannot measure everything. In chemistry, there is also things that is not possible to measure. Concentration of they are conceptually there, but or we have to destroy the system. understand what I intend. We are here not destructive. I mean, we measure what we want, what we can, and then we get information what we don't want or we don't can. Now it's the example, I have it is a Yuku, but I don't know where. This is very interesting because where is Yuku? What do you have to measure? It doesn't matter. No? We measure the current, then we estimate Yuku and omega. Could be an exercise to do at home. And in chemistry, not the system is more evident this. And also in chemistry, not destructive means how was destructive? Understand what I intend. First of all, destructive means offline. It's not the system is not running. I open everything and then I get information. But this is once, and then during the process, change everything. And then you cannot use. Or destructive sometimes that you have to really to implement, to use some sensors with Niels Werner, we work together on the camless system and a motorway without cam. And we have to control the new cam, which is an electromagnetic actuator or the valve. And we need position of the valve and velocity of the valve. You can understand that if you go to within a resistor and a rheostat close to the ventil, to the valve, the temperature does not allow that in a few hours the resistor is broken down. This means we have to consider in a current far away from the valve, which feed the valve, and through the current we have to estimate position, the velocity. How is possible to measure on the cylinder? This is the temperature. This is not allowed. To put in okay, we can say we put in a resistor far away, but the resistor does not move. And I mean, we measure nevertheless the current. And measuring the current could be done also with a shunt resistors or something like that. But we measure the current. The idea is somehow to put something which moves, no? But close to the moving part, which is the valve on the cylinder. How one can do that? Destructive is not possible to do, or something really strange. Or to broken down the system somehow. I'm not expert in the sensors, no? Because we try to minimize the sensor we have seen. This means, yeah, just a second, let me open, yeah, extended R. Look, I will share the M file. I don't need to explain, I think it's exactly the same, but it's useful to go to the right folder. I will upload everything. Now, let me open this. Where is it? Extended Kalman filter, as I told you, using through an augmentation of the state. We fell down is nonlinear representation. What is interesting for us, it doesn't matter if the system is linear or nonlinear, it's the representation. Keep in mind this. Also in the test of the observability, we don't test the physical observability. We test the representation of it. Because the physical system does not exist. I mean, God knows where it is. I don't know, it is a little bit crazy, but it makes sense. I was in a dinner with a mathematician together with my wife. And the mathematician told me, we have to, Paolo, we have to converge as soon as possible to the virtual surface sliding mode. And then I said to me, the virtual surface doesn't exist. My wife looked to me, this distance, we converge, we reach something which does not exist. Therefore, probably the difficulties in this course is a little bit another language, a little bit extremely abstract. No? We are looking for something which does not exist, but just in our fantasy to describe something which I assume that we perceive. And something which cannot work. Kalman field cannot work. A little bit strange, no? But it's interesting, believe me. Okay. basically, what is the difference here? The difference that here I have a resistance with I don't know the value. The value is in the M file 12, no 11, excuse me. Here inside I put another value, and if you look inside at this again interpret file, it's 0, I think. Look what happens. The rest is the same. Of course, everything is now a 3 times 3. The covariance matrix 3 times 3 because we have 3 states. The last state, R, is an augmented state. Does not exist as state, but it's our augmentation because as a state, we have the possibility, if the system remains observable, to estimate it. Because for Kalma, it doesn't matter if the state exists or not. In the equation, once you put with the derivative, it's a state. Remember my concept of the state. Because if change, please pay attention to this concept. If something changes over time, this parameter changes also the energy of the system. But this is clear. If the temperature is there, at this moment, the temperature is not considered as a state. Otherwise, R is the function of the state temperature. And the temperature is a new state. Always in a linear system. Because R multiply the current, but of course, in this sense, R is in a function of another state. Could be an interesting also project for, let me run, then we will analyze. It's also interesting the sentence of the mathematician. We have to reach, in any case, a surface which does not exist. The virtual surface in the slide does not exist. It's not a surface. It does not exist. But we have to reach. My wife said that this is a little bit what happens. And then we clarify that we are working. Yeah, it's not so nice. It could be improved, but I don't want to try to do it. But look, the error was very, very large, I think. No? Let me see. Basically, I put an error, it doesn't matter what. Let me see if it's correctly represented, because also this could be also a problem. No? It's correct. This is the actual value initial, because here we have the initial value of x. Let me. What I'm doing now here. Oh, okay. It seems to be slow. Not 2 seconds. Anyway, you can try to. Yeah, look. Let me see what I put here. Seems to be here. 0, it seems to be. Let me look exactly. Let me look exactly what I wrote in the initial value. This means let me go here in the M file, which is where is this one? No, excuse me. Yes, it's not embedded. Yeah, is that I copied basically here. Nevertheless, I would like to show you this. I copied here exactly what I told you. In particular, do you remember this a priori estimation of the state? This is in the field. No, the word field. You can see there's no linearity. No? The current, which multiply the resistance. The sense is no linear. No? R here. Because here we have a look, three variables in the vector: the current, W, and R. X star is exactly my, let me show you. The lecture is the lecture. Did you see the lecture here? I close the lecture, I open up here. It's exactly this. Yeah. Here's my X. I called in the file, let me see. Xter. Huh? It's also it's the copy of the file of the mat of mat. Yeah. Then I do the Jacobian, which you can see here. Anyway, it's basically copied. This is external. The Jacobian. Calculated, basically copied from the lecture. Yeah, that does not change. Very important, instead of A, I have exactly the Jacobian. Now, to show you exactly what does the Kalman filter, and then we conclude really, I have to go here. Is this one? No, it's this one. I think it's this. Yeah, let me see. I put 0 resistance, and the error, yeah, extremely large. This means you have seen the reaction extremely. How to tune this? There is also criteria. No? The relative criteria between, I don't have time to tell you, but typically then we have to consider an algorithm that is monitoring what I am doing with respect to the measurement and update you. This is fixed once, just at the beginning, then the effect of this slowly will disappear, but the beginning is strong. The first 2 or the 3 steps. Because this pk-1 at the beginning is p0 and influences p minus. And p minus influences k. But of course, then during the updating will be updated pk-1. And typically we try also to adjust the Q and R with algorithms, neural networks, or we use more than neural network particle swarm optimization methods. Now, if I look at the reaction should be slow. Oh, a little bit slower, no? Try to tune the Kalman filter at home. We can. It is a little bit better than before, no? But it works also if I say something not realistic. No? If I put an initial value of the resistance negative, this is physically not possible. We can see that it converge. Do you want to see negative values? Yeah. You believe me that we get the results. Because the Kalman filter, it works even though we do some stupid error, no? Because a negative initial value of resistance. Let me show you this, and then we will conclude with this last. Stop the simulation. Yeah. No? Where is? Instead of 0, which is still stupid, no? -10. I don't know if it's worked. I hope. Okay, no? It could be that doesn't understand. No? I mean, why I don't understand? Because the problem is not convex. Net optimization problem. This means solution exists and not exists. Look, so relatively robust. But at the beginning it was no, better before, but I understand. Kalman filter doesn't work, but we can see that can help. No? Okay, I would like to conclude here for today. Concerning the project, you don't have problems, but too easy was, no, for you. Osama, questions?
Thank you.
Okay.
Thank
Okay.
you.
Thank you to everybody. No question about the project. So. Okay. Osama, thank you. Thank you to everybody. We will see what is the deadline at the end of July. No?
Yeah.
Yeah.